All right, good day everyone. Welcome to this IPCOS webinar on improving and sustaining PID loop performance. I'm Edwin Wieting. I'm the Advanced Process Control Business Unit Manager within IPCOS, responsible for IPCOS process control services and products worldwide. I've been active in the process control field since 1992. So more than 23 years. And in those 23 years, I've seen a lot of customers struggle with everything that relates to PID loop performance. So I'm really glad to be able to have a chance to talk to you about PID performance and PID performance maintenance. In this webinar, we'll share our views on and experiences on how different companies deal with PID loop performance improvements and PID loop performance maintenance. I'll start with giving a brief introduction of IPCOS for those of you that haven't worked with us before, and then we'll get into the topic of PID loop performance. I'll discuss how PID loops are being used in practice based on our engagements with many different customers. And I'll also spend some time on discussing how different customers do PID loop performance improvement projects and in order to get their PID loop performance to a high level for the entire plant. After that, we'll talk about the big challenge of how to keep the PID loop performance at that high level. And then I'll finish off with describing some real cases that we see in practice on how different companies have dealt with PID loop performance improvement and maintenance. And as you'll see, some stories are successful and some others are less successful. Just a logistic comment, all participants are muted. If you would like to ask questions, then please do so via your Q&A chat window in WebEx. And I'll address those questions at the end of this webinar. In case we run out of time, I'll make sure to address your questions after the webinar via email. All right, quick introduction to IPCOS. We're a company that provides expert process control services. We combine in-depth process knowledge and operational experience with state-of-the-art process control. Our business is really a people business. The knowledge and experience of our people is what brings value to our customers. So that's why I always show a picture of the team when introducing IPCOS. These are the people that make the difference for our customers. And by the way, the building that you see in the background behind our team, that's not our office. We have 5 offices across Europe, Middle East, and India, but we're really active all over the world, on every continent, although it's fair to say that most of our activities are in the Middle East and Europe. IPCOS is an independent services provider. We provide services to customers for any type of DCS and any type of advanced process control software. We do studies and audits. We do PID tuning, so base layer optimization and maintenance. We do advanced process control, both implementation and maintenance. And we provide training, and the training focuses on PID tuning and focuses on advanced process control. For the APC activities, as I mentioned, we service any type of APC, including DMC+, SMOC, RMPCT or Profit Suite. And we also provide our own APC software called Inca APC. And for PID tuning, we have 2 excellent tuning tools called Inca PID Tuner and Inca Aptitune, but I wasn't going to make this a sales session, so I won't talk too much about those. In this webinar, we're going to focus on the PID tuning, base layer optimization, and maintenance. Who do we work for? This is just a subset of our customers. We're very proud to show this slide with some of our respective customers, and you'll probably recognize many of the names. For us, honestly speaking, what is even more important is that we're very proud that more than 70% of our customers have been with us for way more than 5 years. And in our view, that means that we're doing something right for them. All right, enough as an introduction to IPCOS. Let's get into the topic of the webinar now, PID loop performance, how to get it up to high levels, and how to keep it there. Now let's start by recapturing why plants use PID control. Of course, the two main reasons are to provide basic stability to the process and to decouple the process. And let's take a minute to think what this means. Basic stability means doing automatic corrections in case of changes in the plant. And this could be rejecting disturbances, like if it suddenly starts to rain, then you'll see variations in the overhead condenser of a column, and this would impact the temperature profile in the column. And a PID loop could help correct that automatically. Decoupling means that you make it easier to control the process parameters individually. And those process parameters are very often coupled from a process point of view. Again, let's take the example of a distillation column overhead. The pressure and the temperature in the top are very interacting. If the pressure changes, the temperature changes, and vice versa. And with PID loops, you'll be able to keep the pressure and temperature stable and set their target values more or less independently. Now, in the ideal world, you would like your process to run steady with no disturbances and without the need to make any changes to the process parameters. It almost looks like a straight road ahead, clear blue skies, but the reality, unfortunately, is completely different. The main reason for the reality being much more complex than that straight road ahead is that most of the process parameters are influencing each other. In control terms, we say that the process is multivariable. If you change one parameter, many other parameters will change as well. And that's one of the main reasons why PID loop performance is something that isn't as straightforward as many people would think or expect. The performance of one particular PID loop will often depend on the performance of other loops around that PID loop. Now, why is this important? In many cases, it might be impossible to tune one loop correctly if other loops around it have not been optimized. And this goes further than just the tuning in auto mode. A PID loop should remain stable even if the other loops around it are taken into manual. And again, let's circle back to that example at the top of a column. And the pressure and temperature at the top of a column, it could well be that if you tune both PID loops very tightly, they work well. But as soon as you take one of them into manual, the other starts to oscillate. And therefore, we consider PID tuning really a multivariable problem. All right. Let's look at how we see that customers use PID loops in practice. We all know that some PID loops perform better than others, and if we walk into the control room of a plant, then we typically encounter one or more of the following scenarios about how PID loops are being used. The first scenario is a scenario that we would all like to have. PID loops are in auto, performing well, that's how we like it. Now the second scenario is a scenario that looks like the first one but is fundamentally different. The PID loops are in auto, they seem to be working well. However, whenever there's a disturbance in the plant, operators take the PID loop in manual, they change the output of the controller, and then put the loop back in auto again. And then when you ask them why they're doing it, they say, well, we're helping the PID loop. So our question would be, who's doing the basic control here? Pretty sure it's not the PID loop. The tricky thing with this is that it's sometimes difficult to see that this is the case until you really sit next to the operators or take a very close look at the data. If you just take a look at the percentage that the loop is in auto, for instance, it will be close to 100% because the operators take the loop in manual just for a few seconds until they've adjusted the output. So there's basically little or no PID control, but you don't see it in the status of the loop. So this is not a good situation. The third scenario is easier to spot. It's a loop that is in manual, and this can be due to a lot of reasons. And one reason that you've probably all seen is that there's valve issues. The valve might be sticky or have significant hysteresis or anything like that. And the question to ask here is whether the valve issue is real or whether a valve is being blamed for some other root cause, for instance, bad tuning of this loop or loops close to it. Because bad tuning is one of the main reasons why loops are being kept in manual in practice. And if bad tuning is indeed the main reason, then that's actually a good thing because it can be fixed quite easily. Another reason why loops can be in manual is actually related to bad tuning, and that's a wrong choice of equation type. As most of you will know, many DCSs have a whole range of different PID equations, and not all control engineers are familiar with the differences between the equation types and when to use one or the other equation. And we know from experience that using the wrong equation can make it impossible to get good PID tuning for a particular loop. Also related to bad tuning, but in a different way, is a very fundamental reason why loops can be kept in manual all the time, and that's the wrong choice of the PID structure. And this relates to more advanced PID structures like cascades, feed-forwards, etc. If you don't choose the right structure, you won't be able to tune the loop. A good example of this is a C3 splitter in an ethylene plant. If you try to build a bottom level controller that is cascaded with the bottom flow controller, you won't be able to get the operators to keep the loop in auto. And the reason is not that the tuning is bad, but the reason is that it's not correct from a process operations point of view to control the bottom level with the bottom outflow of this column. Another example is the situation where a temperature controller is configured to write its output directly to a valve. So instead of using the flow set point to cascade to the temperature controller, the customer chose to have the TIC write directly to the valve because he thought that would provide better control. But he didn't realize that any pressure fluctuations will influence the flow through the valve, which will cause the temperature to change. And if the structure is changed to use the flow controller to cascade to the temperature controller, then the flow will automatically be kept at set point by the flow controller, and as a result any pressure disturbances will have less of an impact on the temperature. This is a very simple structure change that can bring nice improvements in the control performance. The fourth and final scenario that I want to mention here is that is the PID loop that is in constant tuning mode. Believe it or not, but we do see customers where the tuning parameters of loops are changed almost on a daily basis. And this can be done by the control engineer based on operational modes in the plant, or even worse, it is sometimes done by the operators themselves. And I've personally seen plants at which the operators had their own little book with tuning parameters that they believed worked well. And they would put in their parameters whenever they liked it. And obviously that is not best practice. So how do our customers go about this PID tuning activity? The main goal is, of course, to improve the overall performance of the base layer controls of the plant. And what we see is that many sites do PID tuning based on operator request. That's not a very structural approach. Quite often there's no real root cause analysis done. The control engineer only looks at the loop that the operator is complaining about without looking at the other loops around it. And remember what I said at the start, PID loop tuning is really a multivariable process. So you have to take into account what's happening around the process area that you're focusing on. As a result, PID tuning could be improved for today and maybe for next week, but how robust will that tuning be for next month, next crude slate, etc., etc. What we also see is that PID loop tuning is seen as a sort of a regular activity when time permits. Again, if you do this, if you do it this way, then there's little structure to the work. Whenever time permits, the control engineer looks at several PID loops and performs some tuning here and there, and that's the way the PID loop performance is being improved and maintained. Now, these approaches to PID performance improvement don't really bring a lot of structural value. They're spot solutions, really, that might help you today but won't continue to bring value in the long term. And that's a pity because you've spent all that money on a beautiful state-of-the-art DCS, and then you're not getting the maximum value from your DCS in terms of basic control performance. So indeed, more and more organizations realize that there's more value to be had from the DCS in terms of basic control performance. And what's required for that is a focused effort to really optimize the base layer controls. And by focused effort, I mean either in-house or outsourced, but focused, time set aside to do this. And by addressing not just the tuning of the loops, but also the structure of the base layer controls, cascades, equation types, etc., all in a multivariable sense, keeping in mind that the process that you're trying to control is truly a multivariable process in which many things will change if you change just one process parameter. And therefore, you need to have good process understanding if you want to really optimize your base layer control. And we always tell our new hires in IPCOS who are going to do PID tuning that the structure of PID loops is not a free choice. You can't just pick and choose what cascade you build and what equations you use. In a way, you need to listen to the process. The process will tell you what structures to use. It all starts with understanding the process, and that's something we really keep emphasizing. We're talking process control. Now, if you do this structured effort to improve the base layer control performance, what do you get? Well, basically, it's back to the original reasons why you would use PID loops in the first place. Significant stability gains, which can give you higher throughput, better quality, less energy consumption, less alarms, less wear and tear, and less catalyst deactivation due to less excursions, etc., etc., etc. So it will give you good benefits in terms of stability, but it will also give you higher service factors of your PID loops, which will keep your management happy as well. And it will give you more decoupling in your process, which will keep your operators happy. Now, the topic of this webinar is not to discuss the details of PID loop tuning, but I thought I'd still share these best practices with you. Just a quick rundown of some things to keep in mind when doing PID tuning. First of all, always separate safety and control functions. If you have safety functions connected to a particular process variable, make sure that the safety functions and the PID control function are implemented separately, so that if you ever choose to change the PID control structure or the tuning, you don't interfere with your safety functions. Now, this might seem obvious, but we've seen customers confusing the two, let's call it that way. Second thing to keep in mind is know the limits of PID control. PID control is really what we call a CISO strategy, single input, single output. And that means that you can control a single input with a single output only, and not a whole process with one simple loop. And as a result, heavily interacting processes might not be controllable by just using PID controllers. A good example there is an exothermic reactor with inter-bed quench flows. Controlling the bed temperatures is often virtually impossible in a robust, stable way with PID controllers because of the highly interactive dynamics in the process. Needless to say, you need to keep an eye on the type of instrumentation you have and the quality. Consider accuracy, reliability of your instrumentation. Don't over-rely on the instruments you have. This could lead to lots of instability. I've talked about the importance of process versus just control engineering. Think process, not control engineering. Solving a control problem in an industrial plant is not a control engineering challenge, it's a process challenge. As I mentioned, control engineers coming out of university, they've often been taught that control engineering is a matter of using mathematics to solve a problem based on data. And in our view, to exaggerate a bit, that's a recipe for disaster. You have to understand the process and let the process tell you what control strategy is right for the problem you're looking at. Maybe one of the most important ones to keep in mind is keep it simple. And make sure that whatever control structure you build is simple so that people understand it and can maintain it. The more complex the structure is, the less value it will generate in the long term, is our experience. Last but not least, solve, don't relocate. As I mentioned before, a process is multivariable, and as a result, stabilizing the process at one point might push the problem further downstream. You have all probably seen cases where a fluctuating vessel level was stabilized by better tuning of the level controller in the vessel. But as a result, the feed to the column downstream was now much more fluctuating, causing lots of issues in the column operation. So I think that's a nice example of relocation of a problem instead of solving a problem. All right, now let's assume you've done your improvement efforts either in-house or with the help of an outside vendor, and your base layer is in a very good shape. The challenge then will be to keep the performance at that high level. You probably know that PID loop performance will degrade over time. A process is a living thing. You can have fouling and equipment deterioration. You can make small changes to your equipment. There could be operational mode changes. Your catalyst might deactivate over time, etc., etc. And as a result, the performance of some of your PID loops and therefore the benefits you're getting from the base layer controls will decrease over time. So what needs to be done to keep it at the highest level? Well, the most heard question when we discuss PID loop performance maintenance is the question, I've got thousands of loops and I don't know where to start. And the funny thing is that this should not be a maintenance question. If you think that your problem is that you've got too many loops to watch, then you haven't done the first step of optimizing your base layer controls. If you do a thorough initial optimization of the base layer, then you will find that more than 95% of all your loops will stay well tuned forever. And because all of these loops are now performing robustly and optimally, it's much easier to pinpoint loops for which the performance is degrading. Let me give you an example. In a chemical plant, we saw that approximately 40% of the loops were in manual. A lot of the loops that were in auto were in the apparently auto mode, this mode where the operators were helping the loops whenever there was a disturbance. So these loops weren't really controlling well either. And the loops that were in manual were mostly manual due to either bad tuning or due to a bad choice of PID equation. So in conclusion, the plant was pretty much in manual for a large part. And the control engineers at the site did not know where to look first. They had so many loops that could be improved. We helped them with a complete optimization of the base layer controls, and that resulted in more than 85% of the loops now being in auto, and I mean the true auto mode. and the vast majority of the loops that we tuned will stay in auto forever because they are robust and the interaction with other loops is limited. And that means that it now has become a lot easier for this customer to pinpoint the problematic loops. And after half a year, it was clear that there was 9 loops that were requiring further tuning and analysis. So instead of having an enormous amount of loops that required their attention, they could now see very easily and clearly which loops were problematic and needed attention. Now, maintaining the PID loop performance at a high level requires 3 steps. The first step is knowing there is a problem. Because even if operators don't tell you there's a problem, like in the apparent auto mode, there might be issues or let's call it opportunities for improvement. The second step, once you know there is a problem, is analyzing the root cause. Don't just assume that it is just a tuning problem. Understand why the performance has gone down. Is it process? Is it materials? Is it instrumentation? Or is it tuning? And then once you've done that, obviously implementing the solution is the final step, and that solution could be a range of things. It can be tuning, it can be restructuring of the PID configuration, etc., etc. So let's look at these 3 steps one by one. How do you know there's a problem? Well, the first way of finding out is the reactive way, by hearing the operator complain. If that happens, then you know there's a problem. Now, the cost of this method of problem detection is of course very low. The operator tells you and that's it. However, the disadvantage of this method is that it relies on the operators to tell you there's a problem. If they don't shout, you don't know. And if the operators fall back into their I will help the PID loop habit, then you're losing money. The second way of detecting problems is by using PID performance monitoring tools, the so-called closed-loop performance monitoring systems. These systems collect data from PID loops, and they do online mathematical analysis of the data to come up with some KPIs for each loop. The big advantage of these systems is that they do the detection and reporting fully automatically. And also the evolution of the performance over time is visible to the user. The disadvantages are that they generate a lot of false positives, certainly in the beginning, but also later in the maintenance phase, and that causes the control engineers to be overwhelmed by the performance alarms and not knowing where to start. And also, typically, the license cost of these systems is rather high. And then, last but not least, the configuration of these systems requires a lot of services effort, because for each loop, KPIs have to be defined, and typically there's a list of up to sometimes even 80 KPIs from which you can choose, and defining the right KPIs for each loop will make or break the accuracy of the system. The third way of detecting problems is to do a scheduled review and benchmark activity, and during such a focused period, and that period can vary from a few days to a few weeks, the performance of the PID loops is being analyzed and compared against the benchmark performance. And the advantage of this is that the method is very, very structured and focused, and it's very easy to prioritize actions based on economic impact. The disadvantage is that this is typically only done once or twice per year, so any performance degradation between the review and benchmark activities is not detected typically. Now let's assume you know there's a problem, you've identified the problem. Now the question is, what is the root cause? And I keep reiterating how important process understanding is. The root cause must be seen in the context of the process. The biggest pitfall in maintaining PID loop performance is assuming that it's just a PID tuning exercise. And before you know it, you'll be trying to tune a loop that's not correctly configured anymore because the process or the operating point of the plant has changed, and therefore you must consider the process in determining what caused the decrease in performance of the PID loop and decide based on that what the correct action is. Another pitfall that we see people fall into very often is the question whether the performance degradation is temporary or whether it's here to stay. Sometimes PID loop performance degrades because of a temporary situation that will last probably only a few hours or a few days, and it won't happen anytime soon in the future. Our recommendation would be don't try to tune your loop to address that. Trying to fix a problem that only exists for a few days will cause worse performance in normal operations. And please don't build complex structures to address very special situations. Keep it simple. PID loop maintenance is best done on simple structures. If you have PID loop performance monitoring software installed, be very careful about automated root cause analysis. Many tools that are available in the market do automated analysis of the data to tell you that there's valve stiction or simply bad tuning, etc. But remember that this is just mathematics and completely ignores the process behind the loop. So don't simply rely on the automated root cause analysis. The important thing to mention about this root cause analysis step in the process of maintaining your PID performance is that it's typically the most expensive step in the process of performance maintenance. And that's because it requires the control engineer to look in detail into the loop and the process. So you better make sure you focus on the right loops when doing a root cause analysis. And this again circles back to making sure that it's easy to pinpoint the loops that need your attention. And that can best be done by making sure that the base layer is optimized across the board in the first place. And also, at any cost, avoid false positives coming from maybe ill-configured performance monitoring systems. Make sure you don't spend a huge amount of time doing a root cause analysis for a loop that is not really a problem. Now, once you've found the root cause, obviously you can define what the solution to the problem is. And if tuning is the solution, then you need to make sure that you do the tuning in an efficient and a structured way. Don't use trial and error. You'll probably never stop wondering whether it can be better. Make sure you use tools that allow you to do one-shot tuning, including for cascade loops. And make sure that the tool you use allows you to analyze robustness of the loop, including the influence of other loops around it. Again, think of retuning the top temperature controller in a column. You need to make sure that your top temperature controller stays robust and stays stable if the pressure controller in the column is switched to manual. If a new structure of the PID controls is the solution to your problem, then make sure that the structure is simple and logical. And also make sure that the operators get trained. And this doesn't need to be a huge amount of training, but you need to explain to them why the structure was changed and explain to them how to use the new structure. And again, make sure that the tuning of the new structure is done efficiently and robustly, including one-shot tuning for cascade loops. Make sure that you document the changes that you make, and preferably use tools that document the changes for you. In this step of implementing the solution, efficiency is really important. You need to be able to rely on a tool that gives you the optimal tuning and a good insight in the robustness without having to go through an iterative process of trying many different sets of tuning parameters. Now, needless to say, Inca Aptitune is such a tool, but again, I wasn't going to make this a sales talk, so I won't go into the tool. And if you do want to know more about the tool, then just contact us or look at the website for case studies, or our YouTube channel for previous webinars and case studies and demos. All right. We're coming up to the end of the presentation. So what I want to do is I want to share a couple of business case examples. These examples are based on customers that we've worked with or talked to see how they tackled PID performance improvement and maintenance. And some did very well, and others did less good, as you'll see. In this first example, a customer did a complete review and optimization of the base layer in one big project, which they completely outsourced. More than 1,000 loops were reviewed, tuned, reconfigured as needed. The operators were trained, control engineers were trained in using our Inca Aptitude loop tuning package, all as part of the project. And the whole exercise gave them a significant increase in stability, obviously leading to an increase in production and a reduction of the number of alarms, also very important. We're now several years later. They're doing all the PID maintenance in-house. The number of loops that requires their attention is in fact very low, and that is because the tuning that was done in the original project was done very robustly, keeps working well at varying operating regions, and they don't have any difficulty in determining which loops require some attention, because it's very easy to spot those when looking at the key process parameters in the plant. And that's because they took the approach to really look at the entire base layer optimization in the first place. So this customer was very successful to date in bringing the PID loop performance to a high level and keeping it there, thanks to their approach in the initial project. That's the major sort of factor that brought them a successful maintenance phase. This customer in the second example was less fortunate. They purchased a PID performance monitoring package, and they implemented the software in a quick project. For most loops, the default KPIs were automatically set during the install, and no tuning was done whatsoever during the installation project. Now, following the installation, the in-house control engineers were overwhelmed with performance warnings. Huge number of loops was flagged by the system as requiring urgent attention. So they did not know where to start. They did not have enough bandwidth to address all these loops. And their management was hugely disappointed for not seeing significant improvements in the plant performance. And they were asking why the investment wasn't paying back. Now, after 2 years, approximately 2 years, they embarked on an improvement project. With management not willing to invest significantly because they were disappointed previously, the customer took a stepwise base layer optimization approach with an outside vendor, addressing one plant area where significant improvements could be made based on guidance by the vendor. And this improvement was noticed by the management, which then approved that their staff then went on to PID tuning courses and acquired a PID tuning tool. And what followed was a much more aggressive approach in which the other plant areas were addressed. And as the base layer was now optimized across the whole plant, the performance of the CLPM system, the performance monitoring system, started to improve as well. And management was starting to see value from the CLPM system. And the lesson learned here was really that the expectation at the start was that the purchase of a CLPM system would magically solve all their control problems. And instead what it did was highlight that another step should have been taken first, the step of a complete review and optimization of the base layer. And only after that the CLPM system started generating value. Now, the third and last example is a customer who did not want to jump into a large project to optimize the base layer of the entire plant. So we looked with the customer in a first assessment of a few days on which areas in the plant the focus should be. And we concluded that the steam header was the area to focus to get the highest benefits from a limited base layer optimization project. The entire plant was actually suffering from significant disturbances, but we were able to identify that a lot of these disturbances were either generated in the steam header or transferred from one plant to the other plant area by the steam header. And when we did the base layer control improvement project for the steam header, it gave a lot of stability to all the plant areas, and suddenly it became a lot more clear what loops in the other plant areas required attention. And this has then led to further benefits and stability in the other plant areas with limited investments for PID loop improvement projects. All right, wrapping up, I hope that we've been able to show you that the key to a successful effort of keeping up the performance of your base layer control is to make sure you've done an entire optimization of the base layer first. If you just try to focus on some of your loops and ignore the rest of the loops, then you will always struggle to maintain the performance at a high level. We want you to make sure that you know what to expect from software tools. That's another message. Set the expectation right with your management if you're looking at installing performance monitoring software. It won't solve your PID loop performance issues for you. And last but not least, successful PID performance maintenance requires focus, process knowledge, and of course the right tuning tools to work efficiently. With that, I'll open up the floor for questions. I see one question coming in here. So you recommend against performance monitoring tools? Good question. That was to be expected. No, we don't recommend against performance monitoring tools, not at all. But we warn for disappointments because too often we see customers expecting that these tools will solve all the PID tuning problems and cause the base layer performance to increase a lot. And that's not what these tools do. These tools can be a great help, but typically only after you've brought your base layer performance to a good level. And if you install these CLPM tools before you brought the base layer performance to good levels, then you'll simply be swamped by alarms and notifications that your base layer is not performing well. And well, you know already that there's improvement opportunities, right? So you don't need a system to tell you that at this phase. Another question that has come in, you say this is not a sales webinar, but I'm sure IPCOS would love to do an entire base layer project for our site. And I think that's a huge project that we won't be able to justify that. Yeah, we hear that more often. I understand that. Of course, we're not doing these webinars to tell you that IPCOS does not want to do business with you. So yes, we think we can create lots of value by doing these types of projects for you. But many customers have the same budget challenge like you have. So I would recommend that you take a similar approach as the customer in the third example. So identify the key plant area, work on improving the base layer for that, and while we're doing that, we will be able to pinpoint additional areas for improvements. It's the step-by-step approach that we would recommend. Another question that has come in, what are the basic indicators, the KPIs, to monitor PID performance? That's a good question, and really the answer is there is no standard answer to that because it depends on the parameters you're trying to control, the type of PID loop you're trying to control. So there's no one-size-fits-all answer to that. And that is exactly the reason why you see some implementations with CLPM systems not deliver the value that management would have hoped. Because if you use the standard KPIs, the default KPIs that, that these packages suggest, you will not end up with the right performance indications. So again, it needs to be seen in the context of the process that you're trying to control, the type of loop you're trying to control, to be able to say what a good KPI for this, this loop is. Would you do benefits guarantees on PID tuning projects to help justify the investment? Well, that's a difficult one. On our advanced process control projects, we often provide benefits guarantees. For PID tuning projects, that's not as straightforward. The challenge is that in order to quantify the benefits from PID loop tuning, you almost need to do the loop tuning. So the benefits study would be as expensive as the tuning project itself. And I know that in some cases we were able to clearly identify the benefits areas and even quantify them. But in many cases, it's not economically justifiable to do a benefit study first and then do the PID tuning project. However, we do opportunity assessments where we do a quick review of what loops we should focus on in a first effort. And quite often, the customer already realizes that those loops will bring benefits if they're properly tuned. So that then that is the convincing argument to get started on a PID tuning exercise, especially in the stepwise approach, where you start off with a very limited exercise, a couple of weeks, or maybe just even 1 week of doing some loop tuning. That's low threshold, and by doing it, you can prove that there's lots of value to be had from these PID tuning investments, whilst the level of investment for doing that first step is very, very low. Another question that has come in, we have installed a CLPM system in I guess that's 2012, but it was configured with all the defaults. Should we change the defaults? Yeah, good question. I assume that you mean to ask whether you should configure the KPIs for each of the loops instead of just saying staying with the defaults. And as I just mentioned also in the answer to the other question that was asked, my recommendation would definitely be yes. Look at a reconfiguration of the KPIs for each loop. But I would only do that after you've done the base layer improvement effort. If you just change the KPIs for each loop without bringing your base layer performance to a good level, you won't get any value from changing the defaults to loop-specific KPIs. So I would definitely recommend you take plant area by plant area, improve the base layer performance, and as you go, you change the KPIs per loop in the CLPM system. And of course, if you want us to help you, we can. We've worked with many different CLPM systems in our projects before. I think we have time for maybe 1 or 2 more questions. We can do this ourselves, right? Do we need IPCOS for this? I guess the honest answer is yes, you could do this yourself. But what we see in many customer organizations is that it's very difficult to get the time to focus on the job. If you want to do this right, then it's not something you can do in between 2 meetings. It requires several days or weeks of undivided attention in order to create structural improvements. Also, you need to have the right experience, of course. The broader the experience with PID tuning, the easier and more efficient it gets to improve the base layer performance. So I guess, yes, you can do this yourself, but in many cases you could get better results faster by working together with a team that specializes in this and does this stuff on a daily basis throughout the year. All right, given the time, I am going to leave it at that. I see several other questions that are a bit similar to previous questions asked, and I'll address those questions via email. If you would like to receive a copy of today's presentation, then please email me at the email address that you can see on this slide. You can watch a recording of this webinar and previous webinars of IPCOS on our YouTube channel. Just go to YouTube and search for IPCOS to get to our channel. And I also want to draw your attention to our next webinar, which will be held in May. It will cover APC benefit studies, value and methodology. And I'll read out the abstract for you as a teaser. Often APC benefit studies are demanded by customers that are considering the implementation of APC. Different vendors do different types of studies with varying levels of detail and accuracy. In this webinar, we will look at a variety of study methodologies and the value of each of these. We discuss the goals of these studies and conclude on the best practice methodology for APC benefit studies. So that's for the next webinar. We look forward to welcoming you again at our next webinar. And for now, thanks for your participation, and you all have a great and successful day. Thank you.